My name is Helena Vorspohl. I studied mechanical engineering in Aachen, and I'm working for TLK Energy since more than 4 years now. We are doing engineering services and sell software, especially for thermal systems. And today I would like to present our software TIL Adsorption for the system simulation of adsorption processes. And I would like to discuss with you one example. In this case, it's going to be a pressure swing adsorption to gain oxygen. Yeah, maybe we can start with a little motivation, why it's useful to use modeling for adsorption processes. Yeah, first of all, the design of adsorption plants and the process design for gas separation is a very complex task. And we think modeling helps here to gain a better understanding of the process and itself and its interactions. Then we use adsorption equilibrium data and adsorption kinetics of gas mixture. And with the simulation, you are able to extrapolate or interpolate these data. And the experimental based optimization are very time consuming and cost intense. So here actually the big advantage of a model is to do optimization in advance. Yeah, as I already mentioned, today I would like to present a pressure swing adsorption process to gain oxygen. Now first of all, I would like to present our software we sell. Our main software product is actually this TIL Suite. This is a modelical library for thermodynamics systems. So what you can see here on the right hand side, we have an example system, which is in this case a heat pump. And the TIL Suite contains actually a model library with different component models like heat exchangers, valves, compressors, tubes, and so on. We have a TIL media library to provide media data, and also a file reader if you like to check your model or compare your model with measurement data. And for some specific fields, we have TIL Add-On libraries. And in this case, for the adsorption, we are using the adsorption library, where I am actually responsible for. What contains the TIL Adsorption library? First of all, we have a universal basic model to model adsorption equilibrium. We have implemented different isotherm models like Dubinin, Langmuir, Tooth, and also SIPs, or also like new isotherm models for Levatite or something. We are able to simulate different adsorption phenomena like adsorption and desorption, hysteresis, or multi-component adsorption. And we have also component models for an adsorber or different setups of adsorption wheels, for example, to dry air for house or dry room. And we have also different example systems included, like a temperature swing adsorption process to dry hydrogen. That's actually here the picture at the bottom. And the big advantage to use this software is actually that you are able to simulate and analyze the transient behavior of drying and separation process. You are able to analyze breaking through curves and calibrate adsorption kinetics. You are able to change the material of your process very easily, and so you're able to optimize the material cycle times or also the size of your plant. You're able to investigate pressure swing adsorption, temperature swing adsorption processes, and you are able to add your own adsorbent to the library. So that's, I think, a big advantage, that you are not just limited to the adsorbents which are already implemented. If you have isotherm data or calibrated isotherms, you are able to expand the database for adsorbents. Okay, how do we get the information of our material into our library? Therefore, usually we need measurements of isotherms and breaking through curves. We usually do this also with 3P. If we have some measurement data of isotherms and breaking through curves, we are able to fit a suitable isotherm model to these data and fit the kinetic coefficients based on the breaking through curves. And these informations are used to implement an adsorbent based on a different isotherm model, and then we can create a plant model with the components from the TIL adsorption. As I already mentioned, today I would like to discuss the oxygen production with pressure swing adsorption. Therefore, I set it up an example model, which you can see here. So we start here from the bottom. That is actually our source boundary, where we define our inlet conditions to bed system. I used here dry air, so actually the water movement was in advance. We have a temperature of 20 degrees and a pressure of 6 bar. We are using a fan model to define the volume flow rate in our process. Then we have here 2 adsorber. Both of them use zeolite 5A as adsorbent. We are using a bulk density over 700 kilogram per cubic meter. Both have a length of 1.5 meters and a diameter of 0.4 meters. And we can use here a 1D cell discretization in flow direction. And here I used a discretization of 20 cells for each adsorber. Here at the top, actually, we have our sink boundary, and you can imagine after the sink boundary, actually, the buffer tank will follow, which is not modeled here. Of course, I also considered the heat loss to the ambient from the adsorber. So we have a heat transfer from the adsorber to the housing and from the housing to the ambient, of course, for both adsorbers. And I control this process via a state machine. So the state machine actually defines which valves are open, which valves are closed, and how long actually one process step goes. Here you actually can see the details of our adsorber model, which is here on the left-hand side. It considers several adsorption cells depending on the discretization we used. Between these adsorption cells, we have a pressure drop model. To model the pressure drop, here we are able to use different equations. I mean, the main equation we are using here is Ergun equation for packed beds. And each adsorption cell consists actually on 2 cells. This is what you can see here on the right-hand side. So we have one gas cell and one adsorbent cell. And In the adsorbent cell, we actually have our media data from our adsorbent. And now we can define if we like to use the driving force pressure or partial pressure or loading. For the case we are using the driving force loading, we use linear driving force. That means we are calculating with the partial pressure and the temperature, the equilibrium loading, and compare it to the actual loading our adsorbent cell. Is the loading in the gas cell, the calculated one, bigger than the loading in our cell? We see adsorption. Is it the other way around? We see adsorption. Now I would like to analyze with you the process I built up here. On the left-hand side, you can still see the model, which I set it up. On the right-hand side, we see some plots over the time. And first of all, we can analyze the adsorption step. So therefore, actually the gas streams here from the thing through the fan, through valve 1, through our adsorber 1, to valve 7, and then goes into our sink boundary. Here on the right, we can see actually the state. State 1 equals the adsorption phase, which is in this case more than nearly 3 minutes. Then I plotted here also the pressure in our adsorber. During the adsorption phase, we have a pressure of 6 bar. And here at the bottom, you can see the oxygen concentration at the inlet and at the outlet. So at the inlet, it's always constant, which basically makes sense. At the outlet, we see at the end of our adsorption phase a big increase of the concentration. And here actually we reach in this phase here the purity I need for to gain oxygen. So here we have over 90% purity. After the adsorption step, we do a pressure equalization. That means that just the valve 5 is open. So adsorber 1 is connected to adsorber 2. This is actually a very short phase. I think it's just a few seconds. So here you can see a slight decrease of the pressure, and of course the oxygen concentration is decreasing directly. Then we have a blowdown where we open the valve 3 to the ambient. So the pressure from 6 bar goes to ambient pressure. Now in the fourth step, we have the regeneration or desorption. During this time, the other adsorber is in the adsorption phase. That's why this part is that long. After that, we like to increase our pressure again. So we start with a pressure equalization once again. Now we have a stream from adsorber 2 to adsorber 1. And you can see here already a big increase of our pressure. And in the last step, we increase our pressure again to 6 bar. And start after that once again with our adsorption phase for adsorber 1. So now I would like to analyze a little bit some details of the process. So here on the left-hand side, you can still see our state. Here in the middle, I plotted now the average loading of adsorber 1. And at the bottom, the oxygen concentration, which you could see already in the slides before. So during the adsorption phase, we see, of course, an increase of our loading for nitrogen and oxygen. We have here multi-component adsorption. And yeah, as I already mentioned, just in the last minute, so to say, of the adsorption phase, we gain actually the purity of oxygen which we like to have. So if we like to have a look into our adsorber to a specific time, we are able to plot the loading for each cell. So this is actually now the loading of each cell at the end of our adsorption phase. And what can we see here is that actually the adsorber is just half full, or nearly half full with nitrogen. Yeah, so here in the last 7 cells, we don't see a big change of the loading. And we see actually for the last cells a plateau for oxygen concentration. So we are using here adsorption time for nearly 3 minutes, so 168 seconds. And now I calculated the yield for each cycle, and in this case it's nearly 16 kilogram product oxygen to kilogram potential. So as we can already see here, the adsorber is just half loaded. So the question here is, can we optimize, for example, the adsorption time to gain actually more oxygen with a high purity? Therefore, I set it up a dynamic optimization problem for the pressure swing process. That is now a very simple cost function. So I just wanted to minimize the negative yield, and my optimization variable is the adsorption time. And the only constraint I considered is that I need a purity over 90% for oxygen. And here on the bottom, we actually see the progress of the optimization. So it needs some time, but at the end, 16 steps were used to solve this optimization problem. Now I'm simulated the process once again. With a larger adsorption time from our optimization problem. And what you can already see here is actually the high oxygen concentration is much longer at the end of our adsorption phase. And we can compare actually the loading over the length of the adsorber with the results from the simulation without optimization. So what you can see now here with the increased adsorption time, we use nearly the third of the adsorber, and we can increase the yield more than doubled with this optimized adsorption time, which were in this case now 200.77 seconds. So actually I'm already coming to my conclusion or summary. So the TIL software or TIL adsorption software gives you components to model adsorption plant, and you are able to optimize actually the plant or process. In this case, I optimized a little bit the process design, but you could also imagine to optimize the energy which is used, or the plant design, the diameter, the length, I don't know. And already mentioned, we sell also other products like the optimization suite I used here to model or to do a dynamic optimization suite. And we are doing also engineering services in this field and help customers to build up such plant models. And yes, so thank you very much for your attention, and I'm happy to answer some questions.